yeah, sorry, started moving too late. So this is the 24th day of operations research. We're going to continue our stuff on fixed points today, and we are going to talk about the difference between constructive and non-constructive methods. As a tip to optimization today, I am wearing a medal that I won for solving Rubik's Cubes. It's really nice when you organize the competition. We were hearing some stuff about a North Korean competition today. When you organize the competition, you can create the categories. So there's going to be a Rubik's Cube magician coming Thursday night. I will be talking about how to solve the Rubik's Cube tonight with my kids, Peresky, 7 p.m. The God number for the 3x3 Rubik's Cube is 20. No matter how the Rubik's Cube is mixed up, it can be solved in 20 moves or less if you work optimally. I will not get anything close to that for those of you who come tonight. But I think I will be within a square. So, I think 400 moves or less is definitely doable. Okay. So what I wanted to continue doing is kind of haphazard navigation through analysis in terms of slowly coming up with what do we need to make the subject work. Right? My assumption, and you can correct me if I'm wrong, is that you've all taken real analysis because it's a prerequisite for this course, but you may not remember all of the different terms, techniques, and methods from the course. It also might not have been exceptionally motivated as to why you were doing some of the things you were doing. Why did people choose to codify these definitions? Why did people choose to prove these theorems? And so what I want to do is I want to kind of wander through the proof of contraction maps and other things and see why these are good, useful ingredients to have. All right, so we're doing contraction maps. Trying to see if the light is especially low here. Okay, so contraction maps. So we want f of x minus f of y is strictly less than or equal to c x minus y. And again, you should really think of this as just some distance metric. I'm writing absolute value just for convenience, but we're working on some metric space with c less than 1 independent of x and y. And this should be reminding you of uniform continuity from real analysis, that there's huge benefits when the quantity does not depend on the x's and the y's in play. And we started talking about how a fixed point exists for contraction map, and it's unique. So, theorem, there exists a unique fixed point. If you haven't seen the exclamation point after the there exists, it means unique. And the proof is basically start anywhere and iterate. So what I'm not really telling you much about the space, all we can really do is choose a general point and start flowing. We talked a little bit about, well, maybe if the space is compact, there's a boundary point. And we'll see in a moment if we actually need the space to be compact. So we're going to use the Cauchy criterion for convergence. And so here's the proof. Given epsilon greater than 0, we must find some big N such that mn greater than or equal to n implies xm minus xn, oh, I think we were doing it the other way, xn minus xm is less than or equal to epsilon. How many of you have actually used the Cauchy criterion to prove something that you care about? Okay. How many of you have used this to prove about something that you care about for long periods of time? Here's a result we'll actually care about. The existence of fixed points. Right? So we showed that we could write xn minus xm as xn minus 1 plus xn minus 1, and then minus xn minus 2 plus xn minus 2, minus xm minus, I guess, plus 1 minus xm. And we just kept adding 0. Right? So this implies that xn minus xm is less than or equal to xn minus 1 plus xn minus 1 minus xn minus 2 plus dot 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 plus xm plus 1 minus xm. And then what we did is we used the contraction map, that this is the same as f of xn minus 1 minus f of xn minus 2. So it'll be less than or equal to c, and it keeps propagating down. So I'll let you do the details of the algebra, but after some work, up to an error in index, we will get something like xn minus xm is less than or equal to 1 plus c squared plus c to the n minus m times x, I think, m plus 1 minus xm. And what we do is we just keep shifting things down. So if we have xn minus 1, that's less than or equal to c times xn minus 1 minus xn minus 2, which would be less than or equal to c squared xn minus 2 minus xn minus 3, et cetera, et cetera, et cetera. And so we just add them all up. Well, this will be less than or equal to the infinite sum, which is 1 over 1 minus c, because it's a geometric series and c is strictly less than 1, xm plus 1 minus xm. Right? But now we can actually pull this down. Where should we pull this down to? Yes? I'm sorry. We could go all the way down to x1 and x0. But x1 minus x0 could be very large. Where do you think we want to pull this down to? Well, it probably doesn't even matter. We can pull all the way down. So it'll be less than or equal to 1 over 1 minus c. And now when we pull this all the way down, every time we pull it down, we increase it by a factor of c. So we get something like c to the m minus 1, maybe to be safe. x1 minus x0. And we're assuming that m and n are greater than or equal to big N. So this would be less than or equal to x1 minus x0 over 1 minus c. Maybe I have an extra c from here, and then I'll have something like, no, I'll do it like this, c to the n. Because c is less than 1. Give it this, n minus 1. And now the whole point is this quantity here is fixed. If I want, I can even move one of the c's over here down below and have this, c times c minus 1. This is some constant. C is less than 1, so c to the n is going to tend to 0 very rapidly. Yes?
Are you at all concerned that...
No. I am not concerned at all. Yes?
That so m greater than or equal to n, capital N.
Right.
And you just raise it to capital N, which I guess makes the quantity, doesn't increase the quantity, it potentially decreases.
Right. So, I mean, for instance, if m is much larger than big N, this is actually much smaller than it is. I'm increasing things by taking a smaller power. Big N is less than or equal to little m. And remember, c is less than 1.
Oh, c is less than 1.
C is less than 1. It's a contraction map, not an expansion map.
Oh, right.
Right. Yes. So, again, I may be off by an index. Maybe this is supposed to be an m, not an m minus 1. I don't really care. Yeah. This is the main idea. If you need to prove it carefully, you just go through the steps. I don't really have the desire to track the indices that carefully. I want to just do enough to give you the idea of what's going on. This part depends on n. So now, if you want to find an epsilon, you can find what the n is. If you want to make this, I'm always trying as to how much detail to get into stuff like this. How much do you want to see? Since it's probably been a while since you've done real analysis, I figured let's just do one thing really in detail. So I want x1 minus x0, c 1 minus c times c to the n. I want this to be less than or equal to epsilon. So now I will be able to figure out what n is. So I'll then get epsilon c 1 minus c over x1 minus x0. And then I want to take the log of this, divide by, I think, the log of c, what I want to do. And then, let's see, that's what I want to do. And I would have n would be less equal to this. So there's a negative sign that's going on here. So let's see. So this quantity here is definitely going to be negative. Epsilon is less than 1, so epsilon is negative as well. And so I just want to figure out how I do this. Now clearly, since c is less than or equal to 1, if I take n sufficiently large, this will be less than 1. I'm a little worried because now I'm getting a less than equal to. I don't want a less than equal to, I want a greater than. Right? So one of the things I can do is I can do this a little bit more carefully. I'll do it as, c to the n is less than equal to epsilon c 1 minus c over x1 minus x naught. So c to the n is less than equal to c, and then epsilon c 1 minus c over x1 minus x naught. That's what I want to do. I want to write this whole thing as c to the x. So we take the log base c of this quantity. And so we would have c to the log base c of this quantity. Epsilon c 1 minus c over x1 minus x naught. And now, as long as n will be greater than or equal to this, I'll be fine. What's making this a little bit confusing is c is less than 1. So when I take the log of that in terms of the signs of things. Okay. You just need to take n sufficiently large. There is one danger in this argument. What's the one danger? There's one danger here. So I've tried to distract you. I've tried to hide where I might have done something wrong. I'm getting you ready for the Rubik's Cube Magician on Thursday. How many of you know who the amazing James Randi is? He's a magician who spent his life debunking people who claim to have psychic powers. Two of my friends actually left college to go with him for a year and set up his new institute to debunk cranks. And he's a master at getting you to look at the wrong thing. I wanted you looking at the wrong thing. I did something illegal, yes.
Well, first, I think you wrote c strict less than 1, but I think c is also greater than 0. Right?
C is also greater than 0, yes.
And then also could x1 minus x0 be 0?
Yes! I was trying to see if I could sneak that by you. The whole point was I was futzing around with all this other stuff. I was trying to hide the fact, what if I just divide it by 0? What would it mean for x1 minus x0 to be 0? You started at the fixed point. Okay? If you start at the fixed point and look at the iterations of the fixed point, will that series converge? Yes. And what will it converge to? The fixed point. Right? I'm not that worried if I start at the fixed point. But technically, this is assuming x1 does not equal x0, else it's trivial. Right? If you start at the fixed point and just keep iterating, you will get to the fixed point. And you'll get to the fixed point very fast. Okay? Well done. All right. Any other questions on this? So this proves that any contraction map has a fixed point. We needed to work in a metric space, and we needed to have a situation where the space was complete. So complete means every Cauchy sequence converges. Did we use compactness anywhere? No. We don't need compactness. I often like to assume compactness. I like to work on compact spaces. Often when we're doing this in problems, the space can be assumed to be compact. We do not have unlimited resources typically. Nothing in this argument required compactness. Okay. And then again, I'm not going to do it, but if you want me to, I'm happy to give a lecture or two on applications to differential equations and proving existence uniqueness theorems for differential equations. This is an outstanding application of contraction maps, where you start with a guess, and the guess doesn't have to be good. Now, we did Newton's method earlier this semester. And so in Newton's method, it was in some sense a little bit similar. You start with a guess, and it doesn't have to be that good of a guess, and it will iterate to the solution. It's a fixed point problem. You can interpret it as a fixed point problem. Okay, what I want to do now is I want to talk about how we have some situations where we do not have a constructive proof, but we have an existence proof. So here's one of my favorite games. Dot gathering. There's a lot of different versions of dot gathering games. So I'm going to assume the following. I have one special dot in the beginning, and then I have a bunch of other dots in a rectangular row. I'll do 2 more rows just in the interest of time. And what you do is you choose on turn, choose ij, take all, at, below, and right. So for instance, if I choose this one, I would eat all the dots over there. Okay? If eat last dot, you lose. Okay? So whoever eats the last dot, which is the upper left corner. Okay? So on your turn, you basically kill everything in a rectangle. And if this is the first turn, if somebody then goes here on the second turn, it kills these dots over here because these ones are already dead. Anybody know a particularly bad place to go if you're the first person? I'm sorry? The top leftmost corner? Yes. That's particularly bad as you automatically lose. Can somebody come up with another really bad move? Almost as bad as top left. Right next to it. You know, either of the two next to it, you would then have the next person could then just go here and you would lose. So we now have 2 data points of stupid moves by the first person. Who wants to go first? Who wants to go second? Yes.
I'll go first.
You'll go first.
Can I go?
Anybody want to play, Connor? We need an Indians fan. What do you think our objective is if we're trying to analyze this game?
What's the other person
No, well, I think saying stupid move is a little bit over the top. You know, force the other person into a losing configuration. You know, we want to win. The question is, do you think it's better to go first or second? So it is better to go first. There is a winning strategy if you go first. So I can prove that a winning strategy exists, but I don't know it. So I just wanted to do this as an example of a non-constructive proof. It's not entirely useless, because I know that there's a winning strategy for going first. All right, I'll go first. You know, maybe I'll luck out and hit it. But it's not as useful as actually knowing what that winning strategy is. And so this is a really nice, simple example where I can show you I have a situation where I can prove that something with a desired property exists, but I can't actually tell you what it is. Okay? So imagine if I go here on my first turn. There's 2 possibilities. One possibility is if I go here, the board is now a winning configuration for me. Am I happy? Yes. What's the other possibility? It's not. Right? There's only 2 possibilities. The game is going to end with one person winning after a finite number of moves. So if I go here, either I'm in a winning position, game over, or I'm not in a winning position, in which case B has a winning move. I don't know where B's winning move is. Let's say it's at this point here, I comma j. And so I go here, and then B can go here and put herself in a winning position. What should I have done on my first move?
Just gone where?
Just gone there. So if that was B's winning move, all I have to do is on my first move I go there. There is a winning strategy for the first person. And that winning strategy involves either go in the bottom corner and you win, or if going in the bottom corner is not winning, then just go where B would have gone to win. So as a nice exercise, see if you can figure out what the winning strategies are for various board sizes. Does it matter on how many rows there are? Does it matter on how many columns? Does it matter on both of them? What comes into play? You can run a computer program and do some numerical exploration. But again, when you're trying to find a winning strategy, it could be the case that almost all choices are really bad for player A, but every now and then player A has a right move to make. And so you've got to be very careful about gathering data by numerical exploration. Right. So I really like this as one of the cleanest examples I know of being able to prove that something exists without having really any idea of its structure at all. Okay, so let's go back to fixed point theorems. Oh, bless. So we start off by looking at contraction maps. But I really jumped over simpler cases. So contraction map is a very special function, and we talked about it being on a metric space which was complete. You should really build up small. What's a really good example to start with? If you want to try to understand functions and maps from a space to itself, what would be a really good example to start with? So one possibility is R1 to R1, a map from the real line to the real line. So is every continuous function from the real line to the real line, will it have a fixed point? So let's say f R to R is continuous. Must there exist an x such that f of x equals f of x? I think we already handled this. So what's the answer? No. Take f of x equals x plus 1701. I think that was the example we did. And I think you said f of x maybe plus 5, but. So if we go for the entire real line, it's not going to work. So this might have been why I was in a compact state of mind when we were studying contraction maps. Because I knew that when we didn't have compactness here, things failed. Okay, so rather than looking at a map from all of R to all of R, what should we do? I'm sorry?
From N to N.
What's from N to M?
We're going to map from N to N.
I don't understand what N and M are here.
N to N, the natural numbers.
Oh, okay. So now if we do from N to N, so let's say look at a discrete map. But the same example would hold for a discrete map. So unfortunately, shifting from the reals to the naturals doesn't do it.
So I don't understand. Well, I see that the slope here is 1. So I guess that's why. Why does our theorem not apply? We had less than 1.
We had strictly less than 1. Right. So this is not a contraction map.
But take 1/2 x.
All right, so now you want to look at, say, f of x equals x over 2.
Yeah.
That will have a fixed point. What's the fixed point? That will also have a fixed point. Yes. So let's do this as an example. Let's say f of x equals ax plus b. Then we want x to equal ax plus b. So we get 1 minus a times x equals b. X equals b over 1 minus a. Okay if a does not equal 1. So as long as a does not equal 1, it will have a fixed point. It doesn't matter if I have a half. It doesn't matter if I have twice. But there are issues going on here because I'm working on an infinite space. And again, right now, I really only want to look at a continuous function. This is restricting myself to the class of linear functions. It's not a bad idea to ask, on what spaces do linear functions have fixed points? And in some sense, what this is basically saying is, as long as you don't do something stupid, such as just take your input and shift it by a fixed number, which will force you not to have a fixed point, you'll have a fixed point. All right. Any thoughts as to a restriction we could make? So looking at all of R was bad. Looking at just the natural numbers was bad. Where should we look?
0 to 1.
Yeah, 0 to 1. If it's a finite interval, we can always assume the finite interval is just 0, 1. So now let's look at f from 0, 1 to 0, 1 is continuous. I did not want to start with this deliberately, and I may have to reorder the chapters in the book, because this problem is so trivial here, it can be extremely misleading as to what the subject is like. Here's 0, here's 1, here's 0, here's 1. So this is the point 1, 0, this is the point 0, 0, this is the point 0, 1, and this is the point 1, 1. If f of 0 is 0, do we have a fixed point? If f of 1 is 1, do we have a fixed point? All right, so without loss of generality, f of 0 is greater than 0, f of 1 is less than 1. So we have to look something like this. Here is the line y equals x. We now have to draw a continuous function that starts above 0 and ends below 1, and it can never cross this line. This is proof by picture, right? We have to stay above this line. There's no way to do that. At some point, we have to cross the line to get down here. This is not an epsilon delta rigorous proof, right? If you wanted to make this rigorous, what you could do is you could introduce a new function. So, proof that a fixed point exists. Let g of x be f of x minus x. Note, g of 0 is greater than 0. G of 1 is less than 0. So now what theorem do I invoke? Intermediate value theorem. So by intermediate value theorem, there exists an x such that g of x equals 0. But g of x equals 0 implies f of x equals x. Proof. So it just follows from the intermediate value theorem. Unfortunately, we don't have similar results in higher dimensions. We don't have a quick and easy way to get to those results. Okay? Now, it's worth noting one other fact. What is our conclusion? So what can we conclude in this case? Yes?
That there exists a function.
Well, I'm giving you the function. So I'm giving you a continuous function from 0 to 1 to 0, 1. What can we deduce?
Continuous function on a compact subset of the real numbers has a fixed point.
Has a fixed point. Does it have exactly one fixed point? Maybe. We don't know. Do you know the joke about the physicist, the engineer, and the mathematician on the train in England and Scottish sheep? So they spy a sheep, and the engineer, they notice the sheep is black. And the engineer goes, wow, I didn't realize Scottish sheep are black. And the physicist goes, no, all we can conclude is that this Scottish sheep is black. And the mathematician goes, no, all we can conclude is there exists at least one sheep in Scotland which is black on at least one side. Right? Be very careful when you do things in terms of what you can conclude. Is it possible that we could have more than one fixed point? Give me a function that has multiple fixed points from 0, 1 to 0, 1. Y equals x, right? F of x equals x. Right? So we could absolutely have more than one fixed point. This is very different than the case of contraction maps. Okay? The last thing I want to just remark before moving on to the next section is how do you prove something is a contraction map? How do you prove F is a contraction? So we use the intermediate value theorem here. The intermediate value theorem is a great theorem, but it's not my favorite theorem from calculus. I'll put the fundamental theorem in a different category because it's so important. But after the fundamental theorem of calculus, there's another theorem I love. And it's, in fact, when I prove the fundamental theorem of calculus, it's the theorem I use the most in proving it. What are the big results we have from calculus? We have the intermediate value theorem, and we have, what's the other one? The mean value theorem. So if f is differentiable, f of x minus f of y equals f prime at c times x minus y. So if the absolute value of f prime of c is strictly less than or equal to c, which is strictly less than 1, then a contraction. So this is an easy way to see if we have a contraction. If the function is differentiable and the first derivative is strictly bounded below 1 for all inputs. And c is just some point between x and y. So notice here that the mean value theorem is not constructive. It just says there is some point c lives in the interval x, y. But we don't know where c is. Okay? Yes?
Sorry, just on that last proof.
This one? This one.
Yes.
Okay.
I don't understand how you know that note.
Oh, that note? That's because what we did before is if f of 0 is 0, we have a fixed point. If f of 1 is 1, we have a fixed point. So we can assume we're in this case.
So if you're saying it doesn't cross 0?
Well, I'm saying if the function starts off at 0, we have a fixed point, 0. If the function is 1 at 1, we have a fixed point, 1. So for the analysis, we might as well assume that f of 0 is greater than 0 and f of 1 is less than 1, because in those cases where those fail, then we already have a fixed point. So it's just making the simpler assumption. Okay. Any questions on contraction? Okay. We're going to play the triangle game. So I will be on defense, and I want somebody on the class to be on offense. If you beat me on a 1-to-1 ratio, I will give you an A+ in the class without having to do any further work. That's where I get to do one move for every move you do. If I do one move for every 2 moves you do, you get an A, guaranteed A. One move for every 3 moves, guaranteed A-. One move for every 4 moves, guaranteed B+, no matter what you do. You can take crayons and color on the midterm when it comes. I hate saying this on camera, but I can say, you could even write, Yankees great, Red Sox suck. If I get to move only once every 5 moves, you're excused from all remaining homework for the class. Anybody want to play?
I'll play.
What do you think your chances are of winning?
Very low.
Be more specific.
1 in 6.
Be more, no, 1 in 6 is too high of an estimate. If I'm willing to allow people to write Yankees great, Red Sox suck.
Less than 1%.
I think you could be more specific than less than 1%. What do you think Alex's chances are of winning? 0. Right? When I was in high school, I took a physics for poet class at Harvard, and the professor said, I have complete and utter faith in the laws of physics. And he had a pendulum, and he brought it up to his nose. It's like a 500-pound pendulum, and then he let it swing. I don't have that much faith in the laws of physics, but... So here's how the triangle game works. We label the vertices 0, 1, and 2. On this edge, you can only use 0 and 1s. On this edge, you can only use 1 and 2s, and on this edge, you can only use 2s and 0s. My goal is to make sure there's at least one subtriangle labeled 0, 1, 2. Your goal is to make sure there is no such triangle. So we'll put on a bunch of points. And then I think just in the interest of having the class end, well, we'll do one more level. All right. 0, 1, 2.
So bottom row is all 0 or 1.
Yep.
Right side is 1
One,
or 2.
yep.
Left side is 0.
And the class is allowed to help you. So how many moves do I get for every one of your moves? Do I get 1 move, 2 move? Do I have to let you go once, twice, 2 times? Or if you want, I'm happy to not even play.
I want to play.
I'm sorry?
I want to
No, you can play. I'm saying I'm happy not to play.
What?
I mean, am I allowed to make fun of you?
Yeah.
Okay, yeah. I mean, I've known Alex for years. He sucks at triangles. Squares, circles, I'd be a little bit worried, but I know he has trouble with triangles. It's one of the advantages of knowing someone for years. Your class is allowed to help you. How do you want to start labeling things on the bottom?
Volunteer idea.
All right, come on, let's go fast. Yeah. I'm just trying to make sure at least one triangle has all labels 0, 1, 2 along its vertices.
Does the perimeter triangle?
Nope. It's got to be one of the small subtriangles. And I have so much faith in my knowledge of Alex's inability to understand the triangle that I'm happy not to move at all. How do you want to label the bottom?
All 0.
All zeros. Interesting start. All right. Right side. All 1s. Did you want a 2 somewhere? You're allowed to change your answer if you don't like it. You can stop changing things. How do you want to label things here?
All 0.
All zeros. All right, yeah, Müller.
Oh, 1 on the top.
1 on the top.
Or actually, you can't do that. So it's
Why can't we do? Oh yeah, you can't do 1 on the top. So a 2 over here. All right.
yeah.
All right. What do you want to put the label over here?
0.
0. Why not 0? Oh, because if you put a 0, I get a 0, 1, 2, so I win. If you put a 1, I get a 0, 1, 2, and I win. So what do you have to put here? So we have to put a 2?
Can you put a 1 in
Anything you want on the inside. Inside is free. What do you want to put over here? Which did you say 8? Okay. No, I did say anything. Anything means 1 of 0, 1, 2. It's the original definition of anything, not the modern day expansion. I think we want the exclusive ORs. You know, you can't do a 10. I need a number here before class ends. 0. All right. So now I've got 0, 2. What do you want over here? What do we want? 2. Okay. What do we want down here? 1. All right. What do we want over here? So it can't be a 2 where we have a 0, 1, 2. It can't be a 1 where we have a 0, 1, 2. So this has to be a 0?
No, but I still have a 0 left.
We have a 0, 1, 2. Okay.
I think it's not over.
All right, so if we put a 0, we lose from a 0, 1, 2. If we put a 1, we lose from a 0, 1, 2. And if we put a 2, we lose from a 2, 1, 2. So what this would mean at this point is we're screwed. Or actually, not we. I'm winning. It means you guys are screwed. And we have to go back and change something over here. So I played this with my kids for a while until they realized that, you know, yet again, Daddy has chosen a game where he's always going to win. Those are the best games to play. And unlike the other game we played, the dots game, I actually know the winning strategy. Let you guys go. Yes?
You didn't make this game up.
I might have converted it to a game. This is actually Sperner's Lemma. I've turned Sperner's Lemma into a game. And I think I actually did this at the elementary school, and I took down those 3rd graders. I offered $20 to any kid who could beat me. I was like, oh! I mean, they were so excited. And then they're going, what's that? And I go, it's $20. I go, it's Canadian. So, what do you think the theorem is?
You can't fill in every spot so that you have no trouble.
Yeah, no matter what you do, there's always going to be at least one subtriangle that's 0, 1, 2. And it doesn't have to be the nice triangular lattice like this. Any one works. The way we prove that there's at least one triangle is beautiful. I've already mentioned the idea. I mentioned it yesterday. Any idea how we prove that there's at least one triangle that's labeled 0, 1, 2? It's a very powerful proof technique. It's not an invariant, it was the other thing.
You do it by induction.
Not by induction.
Monovariant?
Not the monoinvariant. Nope. I prove something about the number of such 0, 1, 2 triangles. I prove it's a very special type of number. It's an odd number. I prove that the number of such triangles is odd, therefore it's at least 1. It's a beautiful, beautiful method. Okay? Okay, so then the question becomes, how do we prove that it's odd? Well, partly is we step back a little bit and think, is this really the first problem we should look at? Or is there a version of, say, triangles for beginners? You know, maybe it wasn't fair for Alex, I apologize again, for having him, you know, jump up straight to the triangle. You know, what should I have really played with Alex before going straight to triangles? No, I'm still going to take the winning strategy. I'm still going to take the winning strategy. It's nice to be the professor. We shouldn't be doing it on a triangle. What's the simpler game to play first? Line. So instead of playing the triangle game, let's play the line game. Here's 0. Here's 1. So there's a lot of ways of looking at the line game. Your goal is to prevent me from getting a 0-1 segment. And just as an aside, why do you think I care about constructing a triangle with a 0, 1, 2? What do you think this is going to be related to proving the existence of? This is not so I can feel good beating 3rd and 4th graders at Wes. That's a side benefit. Why do you think I care about something like this? What do you think this is going to be used to prove? What are we studying? Fixed points. This is going to be an ingredient in proving the existence of fixed points for certain types of maps. Okay, let's look at the line game. Okay, line game is much easier. All right, and I think you can very quickly realize that you're screwed if you play me. What do you have to put here? You have no choice. If you put anything other than a 0, you lose. What do you have to put here? What do you have to put here? So you keep walking down like this, and you realize you're screwed. Okay? So do we all agree that there's no way to beat me on the line game? I'm just too good? Let's analyze and see how badly I can beat you. I want to prove that I will always have an odd number of 0, 1s. How many 0, 1 segments do we have right now? 1. Let's add points one at a time. When we add this point, if we put a 0, we don't change the number of 0, 1 segments. We still have one 0, 1 segment. Now let's take a point in between here. If I put this as a 0, do I change the number of 0, 1 segments? If I make it a 1, do I change the number of 0, 1 segments? By how much? By 2. So whenever you add another point with a label, you always change by an even number. So the parity of 0, 1 segments unchanged as you add points. And therefore, you start odd, you end odd. Okay? So then the question is there a way to generalize this and somehow build this up to the triangle? And of course, instead of doing this on the triangle, what could we do it on? What's the next thing? I'm sorry? Not a square. Line, triangle, maybe a pyramid, tetrahedron, is that there should be some kind of n-dimensional generalization of this. So when we do the proof, I'm going to concentrate for the most part on maybe just proving it in 2 dimensions. The idea is similar, but it cuts down a little bit on the notation. Okay, so I think this is a good place to stop. I think it's fun that we can do a lot of this by looking at various games and go beat up some little kids.